If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things that also really helps us out as well. Hi, and welcome to another edition of Easy Theory. So today we're going to look at the longest increasing subsequence problem. And you may think, what in the world is that? So we've actually talked about subsequences before on this channel, but in a different context, mainly that regular languages are closed under taking subsequences of strings. So in order to talk about subsequences, we need to talk about what the difference between it and a substring is. Yeah, a substring. So a substring, actually before I even do that, let's look at a particular string. So let's say that I have the string easy theory for no particular reason. Then a substring is we're going to take a contiguous slice of the string. So think of like a pizza, you're going to take a contiguous piece of the pizza. It's the exact same idea, but with strings here. So the string sy space capital T H E, that is a substring. So what we can notice here is that this thing is contiguous in the original string. So it's not skipping characters or anything. Maybe I'll go to purple. No, not purple. Pink. So then a subsequence is exactly the same idea, but it doesn't have to be contiguous anymore. So let's say I take the capital E, the Y, the T, H, and then the R. So then that string, which is capital E, Y, T, capital T, H, and R, so that is a subsequence. It's just picking some elements. You can think of it actually as just picking a subset of the positions in the string. So this is not contiguous, but it doesn't have to be. So the string we had before, the substring, that also is a subsequence, but the subsequence doesn't have to be contiguous, although it could be. So every substring is a subsequence, but not every subsequence, like this one, can be a substring because it might not be contiguous. Okay, so then what is this problem? So the increasing actually comes from looking at numerical representation of the sequence. And by sequence, you can mean any ordered collection of things. So like a list or an array, it's the same idea. So let's say that we have some array here, and I'm going to make it up, like 2, 8, 1, 0, 4, 7, 10. So what we're asking here is we're going to pick some elements of the sequence. So let's say I pick these ones. So then I look at the corresponding subsequence, which is 2, 4, 7, and 10. Oops, parentheses. So this is a subsequence right here, this thing. So this is I'm just going to abbreviate to subseq to make it easier to write. So this is a subsequence. And we notice here that all of the elements are increasing as we go along in the subsequence. So what we want to know is what is the longest set of, what is the biggest subsequence that I can take where it is increasing the whole way through. So if I was just naive and I just said, I'm going to pick every element. So if I pick every element, then once we get to the 1 right here, it doesn't matter what happens next, this is not increasing because the 8 is obviously bigger than the 1. It must be increasing, and it can't be the same. It must continuously, strictly increase along the way through. So let's just start off by making an algorithm for this. So what we can try is the following idea. So I'm going to call it brute force longest increasing subsequence, which I'm going to abbreviate to LIS. Let's say that we're passed in the array A. I'm going to call the array A. So this is the array that we're given of, let's just say numbers, although it doesn't really matter. Well, what we can do is just look at every possible subset. So no, we might not know exactly what to do. What we'll do is we'll just look at all possible subsets of this and just look at each one and see, is it increasing? In other words, is it already sorted? Increasing. And if it is, we'll just keep track of what the largest one is. So here's how we'll do this. So let's let n be the size of A, the number of elements in A. And then what we'll look at is all subsets from 1 up until n. So for subset size, so that's a variable I'm going to call subset size, starting at 1 and going all the way to n, which is the size of A. Then what we'll do is look at all subsets of A of size subset size. I probably should have picked a better name like SS or something, but yeah. So then we'll look at every single one of them, and what we'll do is if any one of them is in sorted order, and remember that this has to be increasing for this problem, then what we'll do is insert a step right here, 1.5 I'm going to call it. I'm going to have a variable called L to be the largest size for which there is an increasing subsequence. Okay, so I could pick 0 elements. In fact, I can even pick 1 element. That's because any one element by definition is increasing, because vacuously is increasing. So then what we'll do is we'll set L to be that subset size. Because this if statement is just saying, oh, you found a subsequence that was increasing. And we're going up in the subset size from 1 up to n. So if it gets bigger, then we'll modify the variable L here. And then at the very end, the very last step is to return that variable L. So it keeps track of whatever the subset size is, whatever the maximum was that caused it to increase. In fact, there are some other things we can do here, like if none of these right here ever cause the, if none of these are actually in sorted order, there's no point in going to the next level, because if we look at every subset in here and none of them are in sorted order, then if we make each one of those bigger, then there's no way that that could be in sorted order either. So there's an early out that we can make here, but in general, the runtime of this is based on the number of subsets. Okay, so what is the number of subsets? Well, from discrete math, what we know is that if we have n elements and we look at every single subset, at worst, the worst case, I'm going to have 2 to the n runtime. So the runtime of this is big O of 2 to the n. It could be faster depending on the contents of the array, so that's why it's actually big O here. It's not guaranteed to be 2 to the n runtime. It could be much, much, much less, but depending on the early outs that we do here. But just implementing it this way, I can't get any better than this, because I may have to look at nearly all subsets. In fact, you can avoid around half of them, but that still gives us around 2 to the n runtime. So that tells us that we can definitely get exponential runtime, but of course the question is, can we actually do better? So can we do better? And it turns out we can. Significantly better. Like a lot significantly better. So let's actually look at an array A right here. And it doesn't really matter what it is, but let's just say that we have some contents in here. And let's just say we have these 5 elements. And let's look at a different subset, which has the same 4 elements right here, but doesn't include this 5th one right here. Okay, so the only real difference between these 2 subsets is this extraneous element. So let's just say that that one is not included in the green subset here. Well, what could the longest length of this be? Well, whatever it is, it can't be too wildly different from this one, because there's only one value that's different between these two, right? So let's just say that this one is I should actually clarify. I'm looking at this subset, and I want to know what is the longest increasing subsequence among these 5. Well, whatever it is, it can't be wildly different than this subset of green, than these 4 right here. So if this one happens to have the longest one is 2, then it can't be like this one is 4 or 0, right? Because I'm only excluding one element. So it turns out that subsets that are kind of close to each other, that don't differ by very much, are going to have very similar longest increasing subsequences. Okay? So what we're going to actually do is try to phrase this in dynamic programming terms by trying to compute really small subsets and then try to work to bigger and bigger subsets, because if we look at a really small subset and then let's say of size 2, and then I try to expand this to size 3, then the answer is not going to be very different. It's either going to be the same or one more than what it was before, which is actually kind of nice if you think about it. So here's how we're going to actually do this. So I'm going to define a function right here. So I'm going to define lis of a, I, and j. And this is actually a very common strategy when you do dynamic programming. Whenever you want to figure out something on an array, you usually say, I want to define the exact same thing, but on a smaller subproblem, which is the longest increase in subsequence from index I to index j. So the original problem is from the beginning to the end. This is just from some index I to some index j. And then what we'll do is we will relate these types of subproblems to each other and then try to build and build from smaller ones to get a bigger one. So I'm going to define this to be the longest increasing subsequence of A involving only indices between I and j. So it can't, for this particular number, whatever it is, it can't expand outside of the I and j sub-range. Okay. And the original problem, of course, is when setting I to be the beginning, let's say index 1, although it could be index 0, depending on who you're talking to. So I is the beginning and j is the end for the original problem. This is just a generalized problem. So we try to generalize things and then try to relate it to the problem that we actually want to solve. Okay, so let's actually try to solve this. So here's what we're actually going to do. So it's something called recurrences, and it's not exactly the same thing as what we've been doing in the discrete stuff when we talked about recurrence relations, which is figuring out the runtime of things. We're actually looking at how do we relate this to smaller versions of itself. Okay, so here's how we're going to do this: lis, a, I, and j. Well, there's something that's pretty obvious. So if this j parameter goes past the end of the array. So if j is past the end of the array, then we're going to say that that's 0 because it's not a defined index. So there's several things that it could be. So it's 0. Maybe I should do this in a different color. So 0 if j is bigger than the array's length. So if j is an incorrect index. Okay? So the way that we're going to actually do, so there are several ways you can do this. Here's how we're going to do it. So let's actually think about this. Remember that it's an increasing subsequence. So we talked about before, if the element at index I is at least as big as the jth one, then it can't be that we can include anything from index I to index j. Or I can't include index j into here. Okay? So what we're going to do here is the exact same answer if we make j1 bigger, because I can't include index j now. So in the case where index j has value smaller than or equal to the ith one, I can't possibly include j, because if I include I, which I'm supposing I do, I can't include index j. So then that means it's equal to the same problem going to the next index and hoping that maybe that one will be the next one of the subsequence, the subset that I pick. So this is if a of I is at least as big as a of j. Put a dot on the j. Okay, so how do we actually work from here? Well, what we notice is that so here what we're going to do is, in this case, so now we're supposing that a of j is bigger than a of I. Okay, so we're assuming that we can actually include a of I, we're including a of j now, possibly. Well, we even if a of j is bigger than a of I, we still might not include it. So as an example, if we go back to the one we had before, this 8 right here was bigger than the 2, but we didn't include it. And I think this is the longest the 4 elements we picked is the longest you can get. Maybe you can do better, but I don't see how to do it. So we either will include it or we don't. Okay, so let's actually think about it. So let's look at the case where we do include it. So if we do include it, well then that means we get one more than whatever we will do if we include it, but we need to move one index further to look at the rest of the elements also. So we may include those also. So that's actually asking LIS of j and j plus 1. Why those two indices? Because it may be that we will include j plus 1 here instead of j. This is asking if we can include j. We're including j, and then we're trying to move to the next element so we can go through the rest of the elements in the array. So this might be that this parameter is 0 or 1 or 2, we don't know. But we're moving to the next element in the array with the j plus 1 here, and we're saying here by this plus 1 at the beginning, we are including index j. But in the other case of where we're not including index j, it's the same thing as if we just move to the next element to start with. So there are two cases here. So actually, if you notice, these two parameters are the same as these two. Oh, I should include the array A here. I didn't do that. So LIS A of j plus 1 down here, and then a I j plus 1. Well, I don't know which one of the two it's going to be, and I'm always trying to find the longest one possible, so I'm going to take the max of both. And then I'm going to put here otherwise. Okay. So yeah, so here it's saying it's 0 if the index is too far. It's going to be if we just skipped over the jth element and tried the next one, if the jth one is not possibly going to be part of an increasing subsequence, and it's going to be the maximum of not including the jth element and including it. So we're always trying to make the best possible choice, and this works because if we include one more element, it either goes up by 1 or stays exactly the same. So it can't vary wildly too much. So that's great. So if we actually look at these right here, the I and j here can be any possible index in general. So what we see is that there are big O of n squared subproblems, because there are order n possibilities for the first index and order n for the second one. You could prove that more formally, but that's the basic idea. Okay, so how do we actually do this? Because so basically what you do is you try to fill the array in a way so that you always will look at problems that you solved before. Well, an array here, well, there are 2 possible variables here. So what we'll have to do is we'll try to store things not in a single array, but like we did with the Fibonacci numbers, but rather in a table, which is the same idea, but just in 2 dimensions. So what we're going to do here is we're going to have a table, I'm going to call it T of I of j, is going to be some number which is going to be equal to lis a I j, the parameter that we just defined before, the longest increasing subsequence from I to j. So the table is going to store those values for us. Okay, so what are we going to actually do here? So so let me do it this way. So I'm going to have lis is a function, but I'm going to have an iterative version. Iterative. So there's not going to be any recursion here, but you could make it recursive, but I'm not going to make it recursive. And what I'm going to do is I'm going to rely on this table. Okay. So here I'm going to have an array A. So remember this array A is the same as the one here. And for convenience, what I'm going to do is I'm going to say it in English, add minus infinity to the beginning of A. Why do I want to do that? Because it's mainly to make the recursive problems easier. The reason you would want to do this is so that on the ends, you typically will have a variable that goes 1 too far or 1 too far early. So what you do is you try to append the arrays with not the values in the array, but just some value that cannot possibly be achieved otherwise, like minus infinity. We're assuming that minus infinity is not in the array to start with. Okay, well, what we saw before is if the index j was too big, then we'll set the lis to be 0. And that's what you typically do. What you typically will do is, with this table right here, you will put onto the ends of the table, just like we were doing right here, some extraneous values to make the recursive calls easier, even though they're not actually recursive. It's just because the variables might be 1 too big or 1 too small, and it's to make the writing of the algorithm a lot easier. So what we're going to do here is we're going to have the value I here be between, not j, it's going to be between 1 and n, n minus, 1 and n. And the j parameter is going to go up to n plus 1 here. Okay, and then what we're going to do for the second step is we're going to set t of I of n plus 1 to be 0 for all I. So it's just setting one column to be all zeros to make the calls easier when we're going to do them next. So what is the next step going to be? Well, we're going to actually fill the table. And what we're going to do is we're going to work backwards. Because if you think about it, the way that the algorithm worked was to build the array up. Now we're going to actually build the array down, and we'll actually see why that is in a few minutes. So what we're going to do here is go for j is equal to n all the way down to 1. So instead of going up, we're going down. So that means we're starting at the right column and working our way left. But here, instead of having the rows go from the bottom up, we're going to have the rows go from the top down. So for I is equal to, not 0, from 1 to j minus 1. And there's actually a very good reason for this. So why do we want to not have this go all the way to n? Well, if we actually think about it, what we're going to do here is we're actually going to fill the table up in a triangular fashion. So if we actually think of it like this, I need one more here. Okay, so what we're actually doing here is we are going to, we're actually trying to fill this region right here. And if you actually look down this diagonal right here, here. So if we look down this diagonal, this is the I equal to j diagonal. And if you actually look down here, this is where the row number is bigger than the column number. So let me do this in a better color, pink. So down in this area right here, this is where I is bigger than j. And from the recurrence that we did, I can remember the term, the recurrence that we did, if the beginning index is bigger than the other one, than the j index, then we're going to set it to 0. So all of these entries, apart from the diagonal, are going to be 0. Okay? And actually, all of the diagonal ones are going to be 1. Because if the index is equal to, I is equal to j, then we can always pick that one element. So the subsequence's length is going to be 1 in that case. So the only interesting ones that we care about are the ones in this little blue region up here. So that's why we're doing it this way. The j index is going right to left, and the row number is going from the first row down and not going past this diagonal right here. That's why we're doing it this way. Okay, I could go all the way down to n here, but it turns out that we don't need to, and the runtime won't actually be affected by this. It would only give a constant time. It would be 2 times longer to run it that way, but it's just better to think of it this way. We're filling the entries that we actually care about, not the entries we don't care about. Okay, so what we want to do is to calculate some stuff. So how am I going to do this? I'm going to have it be capital A here. So I'm going to have, step capital A. So I'm going to have some values. I'm going to be the existing, not existing. So I'm going to have a variable that is keep j, which is going to be 1 plus the table of j and j plus 1. So that was the recurrence of where we wanted to keep J. Step capital B. We're going to be, so the other case is when we skipped the index J. So I'm going to have a variable skip J, which is going to be just the table of, not J, of I and J plus 1. So just to remember, this is J. Maybe I shouldn't use purple for that. This one is J, and this one is I. They are different variables, okay? Just so that you're aware. Okay, so step C. So then if A of I is bigger than A of J, which is looking at that case of where we can't include index J. So then what are we going to put into the table at row I in column J? That's going to be where we just skip the jth variable, the jth index. So skip J. And then otherwise, we're going to look at the maximum of the two. So remember that recurrence we did where we looked at the maximum of whether we kept index J or we skipped it. So here, T, I, comma J is going to be the maximum of keep J and skip J. And that is almost the whole algorithm. So what do we actually return at the end? Well, what we return is we're computing values all the way through. And what do we want to keep at the actual end? Well, we're actually forwarding the value that we want, the longest increasing subsequence, from the bottom right all the way through this this triangle piece of the table right here, all the way to this first element. So what we actually will return here, so it's step 4, what we're going to return is the table at index 0, not 0, 1, and 1. And I want you to actually figure out why that's actually the case, so put into the comments if you can actually prove why that's the case. I don't want to give away the whole reasoning for that, but that's something I want you to actually prove. So, okay, so what is the runtime of this guy? Well, it's pretty clear that each of these steps right here in the middle, so each of these right here, that wasn't good, that's better. So each of these will take constant time because they're just setting entries into the table and taking maxes of things and all that. The real work is in this part. This part right here, in setting up the table, that's not the main workhorse. It's this one right here. So J takes order n time, and I takes order n time. So n times n is, in fact, n squared. So the runtime here is big O of n squared. Okay, so if n is the number of elements in the array, the amount of time to figure out the longest increasing subsequence is n squared time. Cool. So hopefully that was interesting. Leave comments about the longest increasing subsequence down into the comments. God, long video. There are many links in the video description if you want to support the channel, such as liking and subscribing. Commenting really helps too, and I really do encourage you to like and subscribe. It really helps us out. And as always, I'll see you next time.